This is a video to go over lesson 4.3 part 2. So in the first part, let me just quickly review. We were looking at how the first derivative affects the shape of a graph. So the first derivative tells us whether the graph is increasing or decreasing. Today, or in this video, we're going to look at the second derivative and how that affects what that can tell us about the shape of a graph. So there's a new word for us to learn here, and I'm going to highlight all the new words in green today. Concavity. So nonlinear graphs, they can be increasing or decreasing, but they also have concavity. So concavity tells you whether the graph is sort of a U shape or sort of an N shape. So, or happy face or sad face, I like to sort of think of it as. So these are the two different types of concavity shown here in the two graphs. So concave upward graphs look like a happy face. Okay, I'm just going to add to this line so that, okay, so they look like a happy face. So I'm going to be highlighting our happy faces in yellow just because that reminds me of happy. Okay, so that graph is concave upward. And a sad face shaped graph is concave downward. Okay, and the second derivative will tell you whether a graph is concave upward or concave downward. And graphs can switch, functions can switch between the two. They're not always just one or the other. And we'll see examples of that today. Okay, so when we're looking at the second derivative, it's the derivative of the derivative. And we denote it like this. Okay, with 2 primes instead of 1 prime. So it tells you how the slope of the tangent is changing with time. So if we look at the slope of the tangent of this first yellow graph here, it starts off pretty shallow, so the slope would be small, but then you can see it gets steeper and steeper. So it's getting larger and larger and larger. So that means the slope is increasing with time. So that means the second derivative would be positive because the slope is increasing. The slope of the tangent line is increasing. So wherever the graph has a positive second derivative, your slope is going to, you're going to have a concave upward shape. Okay, so a U shape. Concave downward is the opposite. So you can see here the slope of the tangent starts out quite steep. So a larger positive number, and then it gets shallower and shallower, so less and less and less. So the slope is decreasing. So that means that the rate of change in the slope, the second derivative, would be negative. So wherever you have a negative second derivative, you're concave downward. So that's what this says in the box here. Okay, so wherever you have a positive second derivative, the graph is concave up. So you can think of positive as like happy face. That's how I remember it. If the second derivative is negative, you have a sad face shape. Okay, concave downward. Graphs or a function can switch between concave up and concave down or vice versa. So when that switch happens, you have what's called an inflection point, which is another new word for us today. Okay, so let me draw you an example of an inflection point. So let's say we have a concave upward shape, and then it switches to concave down. Okay, that point at which it switches, so here it's concave up, and then here it's concave down. Okay, that point there, I'll label it in green. I'm just gonna use this pen so I can have an arrow. That point there where it switches concavity is called the inflection point. Okay, so we're going to be able to find that point when we do our second derivative test. Concavity can also tell you whether you have a maximum or a minimum point. So it can kind of be a confirmation of the first derivative test. So let's say you know you had a critical value where your first derivative was 0 and you weren't sure whether it was a maximum point or a minimum point. Look at these points here, the valley and the peak of these graphs that I've just pointed to in red, where the derivative would be 0, right? If you have a concave upward graph, that means you have a minimum point, right? It has to be at the bottom of that valley. And then if you have a concave downward graph, that would have to be a maximum point. So it can also confirm what you found in the first derivative test. That's what it has in this third box here. Okay, so we're just going to practice by doing a quick example. I picked this example because these can often be tricky. Okay, so here we are shown a graph, and the graph is actually of the second derivative. So sometimes you know information about the derivative or the second derivative and you don't have the actual function in front of you. So this graph is positive between 1 and 4, and then from 4 to 7, and it has negative values for x less than 1 and x greater than 7. So the question A asks, on what intervals is the function f of x? Remember, we don't see f of x here. We just know, have information about f double prime of x. On what intervals is it the original function concave up? Well, concave up would be wherever the original or wherever the second derivative is positive. And so therefore, it would be for x, so between 1 and 4, and between, 4 and 7. Okay, just make that blue. On what intervals is the, and notice I didn't say at 4 because 4 is where the second derivative is 0, so it doesn't really have concavity at that point. This would be where the second derivative is less than 0, concave down. So we'd be looking at points where x is less than 1 and x is greater than 7. The actual math equations, there we go. Okay, and state the x coordinates of any inflection point. So there's that new word again. So remember that means wherever the concavity of the graph changes. So wherever it goes, wherever the second derivative goes from negative to positive or from positive to negative. These points would be right here and right here, right? So there are places where the second derivative is 0 or undefined. Not always, like it's not always the case where it's 0, it's going to switch, but those are places where it could switch. So we can see it switches from negative to positive at x equals 1. And x, I'll just do this, and x equals 7. Okay. So this example sort of shows you what information you can get from knowing about the second derivative. So you can tell the concavity and you can also find inflection points. Okay, so that was example 2. We're actually going to go back to example 1. So example 1 we started in the first video in 4.3 part 1, and we did the first derivative test on this polynomial function here, 1 over 4 x to the power 4 minus x cubed. And we determined where this function was increasing and where it was decreasing, and we found some extreme values. Now we're going to do the second derivative test on this function and see where this function is concave up, concave down, and where the inflection points are. I'm just going to go back and save some time here by just copying my first derivative because I don't want to redo it. That there. So we found the first derivative already back in part 1. Now we're going to find the second derivative because the second derivative is what tells us information about the concavity. So to get the second derivative, you just take the derivative of the first derivative. So it would be, so the derivative of x cubed is 3x squared, and the derivative of 3x squared is 6x. Okay, and we're looking for possible inflection points. So we want to find points where this is 0, that where it's 0 could be places where it changes from positive to negative or vice versa. So I'm going to solve this for 0. Oops. To find possible inflection points. Okay, because that's where it could change signs. So to solve for 0 here, we need to factor. So we'd be taking out a 3 and an x from both terms. So we'd be left with x in the first term and 2 in the second term. And then we can see what the solutions are. So x equals 0 and x equals 2 are possible inflection. Okay. Now we're going to go ahead and make a table very similar to the one we made in example 1 and look at the second derivative before 0, between 0 and 2, and then after 2 to see whether it's positive or negative. So I'm just going to put the table underneath here. So I need 6 columns. Okay. So here are my x values I care about. I care about x less than 0, equals 0, x 0 less than x less than 2, x is equal to 2, and x is greater than 2. I'm just going to make this a bit smaller so it fits nicely. There we go. Okay, cool. And we're going to look at the second derivative. We already know the second derivative is 0 at x equals 0. And we already know it's 0 at x equals 2. But we want to know whether it's positive or negative between these points. Okay, so again, we pick a test value. So you pick anything less than 0 that's just easy to plug into the second derivative. So you might, for example, test x equals -1. Okay, you can pick any value, but -1's an easy number to plug in. So you could plug it into, the second derivative and see whether it's positive or negative. So we get 3 minus sorry, 3 plus 6, so it'd be 9. So that means the second derivative is positive in this region. Can't change signs in that region because it's never equal to 0. So if it's positive at -1, it's positive in that entire region. Okay, the only places where it could change signs are at 0 and 2. All right, and then between 0 and 2, a nice easy number to test might be 1. Just going to double check that I'm doing this right. Yeah. So we test 1 and we get 3 minus 6, which is -3. So in that entire region, the second derivative would be negative. Okay, and then again, we test a number. It could be anything, and you don't have to write the test number you picked down. You can just write the positive or negative sign if you're comfortable doing that. I'll just put 3. Here's where I need my calculator because I'm not the greatest at mental math. So I'd go 3 times 3 squared minus 6 times 3. Again, so that's a positive number. Okay. So what do these tests tell us about the graph? So what do they tell us about the function f of x? So they tell us the concavity, but they also indicate which points are inflection points. So I'm going to go back to my highlighter again. Here, the second derivative was positive. That means the graph is concave up for all the x values less than 0. In this region, so I'll just highlight this whole thing. In this region here, the second derivative was negative. So that means that for that entire region between 0 and, maybe I will highlight after, between 0 and 2, the function would be concave down. And again, here it's positive, so it'd be concave up. Okay, so it switches concavity at both points. It doesn't always switch concavity at the possible inflection points, so you do have to check. But in this example, both of these are inflection points, so I'm just going to label them IP and IP. Okay, so that's pretty much enough to answer the question here. The question asks, in what regions is this function concave up and concave down? Okay, we've shown that. And where are the inflection points? At 0 and 2. Okay. I'll just summarize here. a function is concave up for x less than 0 and x greater than 2. The function is concave down for 0 less than x less than 2. The inflection points occur at x equals 0 and x equals 2. Okay, so there we go. So just to summarize, if you want to know about the concavity and find inflection points, you find the second derivative, find where that derivative could change sign. So this could be where it's 0 or where it's undefined. In this case, this function is always defined, so we just search for places where it's 0, and we found 2, x equals 0 and x equals 2. And then we did our tests, and we found where it's concave up and where it's concave down and our inflection points. Okay, one last example here. This one is a little bit trickier to find the derivative of. I'm going to use my pen to do this one. So I want to show another example because it's a little bit different. So we're finding any inflection points here. So we're going to find, the first derivative. So this is a product, so we're going to use the product rule when we find the derivative. So we'll do the derivative of the x to the power of 2/3 first. So 2/3 would come down and we'd have x to the power of negative 1/3 times x minus 5. And the derivative of x minus 5 is just 1, so we just have plus x to the 2/3. Now we did one like this in the last section in 4.1, and the trick was, this is really difficult to find places where it's 0 or undefined. So what you want to do is write all of the exponents as positive numbers by putting them in the denominator and then combining it into one fraction. So I'm going to rewrite this first as 2x minus 5 all to the power of 3x, now it's not negative anymore, in the denominator, or 1/3. And I still have 2 terms there, so what I'm going to do now is multiply this one. So this one is over 1 over here. We're going to make the denominators equal. So we're going to multiply it by 3x to the 1/3 in the numerator and the denominator. That's like multiplying by 1, so it's not changing anything. I'm going to expand this bracket as well so I can collect like terms. So we did this again. We did this in 4.1 as well, so if you need extra practice, go back to that example and check that one out too. And this would be, so when you add those exponents, they equal 1, so it kind of works out nicely. Okay, and now we can combine those. So I'd get 2x plus 3x, so 5x minus 10 in the numerator, and in the denominator 3x to the 1/3. That kind of looks a lot nicer than the first expression there. Okay, we don't really need the first derivative for this example because it's just asking us for inflection points. So now we're just going to go ahead and find the second derivative. And since we have a quotient, I'm going to use the quotient rule. So I need the derivative of the first, the top, so it'd be 5 times 3x to the 1/3. And then minus 5x minus 10 times the derivative of the bottom. So the 1/3 would come down and actually cancel with that 3. So we would just be left with x to the negative 2/3 as the derivative, and all over the denominator squared. Okay, again, that looks pretty messy. The trick for this one is to, again, get rid of this negative exponent. You can't just flip it into the denominator though, because that negative exponent is only attached to this one term. It's not attached to both terms. So in this case, the trick is to multiply the numerator and denominator by x to the power of 2/3. And that way, at least, they'll kind of cancel out there. So you have to do this to all the terms in the numerator if you're going to do it. Okay, so The first term in the numerator becomes, so I'll expand it out too. So 5 times 3 is 15. And then remember, you add the powers. So 1/3 plus 2/3 is 1. So you just get 15x. And the second term is really nice. So you'll have minus 5x minus 10. And negative 2/3 plus 2/3 is 0. So you just have x to the power of 0, which is 1. So I'm not even going to write it down. And then all over 9, and then we add the exponents there, so we get 4/3. Okay, I'll just rewrite this without the bracket. So 15x minus 5x plus 10, all over 9x to the power of 4/3. And just combine the like terms. Could have done that in one step, I guess. 10x plus 10, all over 9x to the 4/3. Even better, maybe I'll factor the numerator just so we can see where it's equal to 0. So it'd be 10x plus 1, because there's a 10 in each term. 9x to the 4/3. That's a lot of work for one derivative, or two derivatives, I guess. So let's just review what we did there. And this will happen anytime you have a fractional exponent. These are going to be the kind of tricks you want to use to simplify it. So first we did the first derivative, and we simplified it by getting rid of any negative exponents and then combining the fractions together. And then we found the second derivative using the quotient rule. And this time we got rid of the negative exponent by multiplying the numerator and denominator by the exact same power, but with the opposite sign exponent. And then that kind of canceled those out. And at the very end, we factored the numerator because then we can tell where it's 0. Okay, so this is our second derivative. Let's just focus on this now. So we want to know where this can change signs. So possible inflection points, maybe I'll just type this out because it'll go a bit faster. Possible inflection points occur where f double x equals 0 or f double prime x is undefined. Because that's where it could change from positive to negative. So there are 2 points we should be concerned about here. One point is at x equals -1, because that's where the numerator would be 0. So it would make the entire second derivative 0. And that at x equals 0, the denominator is 0, so it'd be undefined there. So therefore, possible inflection points are at x equals 1, where f double prime x equals 0, right? Remember where the numerator is 0, so -1. Yeah, because -1 would make that 0. And x equals 0 in brackets where f double prime x is. Okay. So those are the 2 points we need. So we're going to make that little table like we did before. I'm going to make it 6 by 3. So these are going to be my x values. So x is less than -1. X equals -1. -1 less than x less than 0. X equals 0. X is greater than 0. F double prime x. Okay, so here's where you need to test. So remember, just pick any value in the region that's easy to test. So I'm not going to actually tell you what the numbers are here. I tested -2, and I found the second derivative was negative. At -1, remember, it was 0. I chose to test -0.5 in this region, and I found that the second derivative was positive. And here we had it. The second derivative was undefined at 0, and for greater than 0, I chose to test x equals 1, and I found that it was positive. So that means our function is concave down, up here, and concave up here. So only one of these possible inflection points turned out to be an actual inflection point, right? So this is why you need to actually do the test. So here it was concave down for less than -1. Then it's concave up in this region and still concave up here. So therefore, conclusion, right? So the question asks, where are the inflection points? The only inflection point occurs at x equals -1. Okay. All right. And I just want to show you what that quickly looks like, so how you could check your work on Desmos if you're sort of unsure of your answer, right? Because that was a lot of algebra to do here to simplify these. So it's definitely easy to make a little error somewhere. And if your answer doesn't match the answer key, then it's like, okay, you need to go back and find out what's going on. So let's go to Desmos. I'm just going to plug in the function. So it's x to the power of 2/3 x minus 5. Okay, and let's have a look at this graph. So you can see here that it's kind of hard to see because it decreases so quickly, but it is concave down for this sort of region here. It's undefined at 0 because it's got a corner at that point. The derivative's undefined there. And then it's concave up, a happy face afterwards. If you want to know the regions where your graph is concave up or concave down, have a look at what I drew on the side here. So I typed in the same function f of x, and then if you use curly brackets, it shows you, like, it gives you conditions. You can write down a condition. So I'm only going to graph f of x where the second derivative is negative. So I want to know where this graph is concave down. Have a look at this blue line. So the graph is concave down everywhere to the left of x equals -1 there. So you can see we got the question right. We didn't make any mistakes. And then the graph is concave up for all of these values here in orange. They don't have yellow, so I used orange instead. Okay, so in the brackets there, I had the condition that the second derivative was positive. So that's a really cool way to check your work. You can see using Desmos where it's positive or negative, and then you can see if you made your table correctly, right? And here's the inflection point at -1, -6. All right, so that is it for concavity in the second derivative test. I'm just going to end the recording.